Just for introduce you today, this webinar is on the frame of an Horizon 2020 project that is finishing this month, that it's called MARBEL. And in this project today, we will focus on all those aspects of the project dedicated to the application of circular economy and eco-design principles in the design of electric vehicle batteries. Okay. As you see in the logos, this webinar has been organized by some of the partners of this project. EURECAT, the research and technology organization in the region of Catalonia, in northeast Spain, and also IREC, Institute for Energy Research in Catalonia. They both have a joint research initiative. It's called BATEC, covering the whole value chain of the batteries for electric vehicles, from the material design of batteries, recycling. Both research centers have pushed for this initiative in a regional level for covering all the value chain of the batteries and providing research services to the industry. And then together with us, there is the contribution of another partner of MARBEL. It's called ecodesign from placed in France. Okay, so let's start with the webinar. As you will see today, I will introduce myself and the project. As you can see, my name is Edward Piqueras. My background is a Master of Science Engineer in Industrial Engineer from the University Polytechnical of Catalonia, and I've been the coordinator of this project, and I work as European Programs Manager in the EURECAT Technology Center. I will introduce the project, and later and after this, we will tackle the core topics of the webinar related to, from one side, the safe and efficient opening and recovery of the battery packs, what technologies have been developed by partner ecodesign in what concerns the end of life of the batteries and the dismantling and recovery of critical elements and materials. Then we will address the eco-design in MARBEL, so in MARBEL battery pack, how we implemented the eco-design when designing the battery pack in MARBEL. We will present the design of the battery pack prototype in MARBEL, so you will see what some of the eco-design actions that we applied. Then we will present the life cycle cost, okay, in comparison with commercial electric vehicle batteries, and we will have some space at the end to take questions from you, from the audience. For us, it's very important to also collect feedbacks and feedback and be able to answer questions from you. Okay, and with this we will close the webinar at 1 the latest. Okay, so welcome everyone to this webinar, and I hope you enjoy the contents. Okay, let's start with the brief presentation and overview of the project. Okay, as I commented, I will be presenting this. I've been coordinating the project in the last 4 years, and this project, as I commented to you before, is a project from the Horizon 2020 Research and Innovation Funding Program in Europe, and we have been working together. These partners, 16 partners from different countries in Europe. And well, as you see, we team up different partners from the research centers and universities in different countries, from tier ones, providers of materials, housings, aluminium, and also components for the electronics for the BMS, etc. And we counted also with a battery recycling company that is presenting today. And our reference OEM was and is Stellantis, okay, the Centro Ricerche Fiat in Torino, Italy. The goals of the project I presented here, briefly summary. We were driven by the topic of the Horizon 2020 program, and the goals were to, from one side, to accelerate the mass market take-up of electric vehicles in Europe, and this mainly tackling those concerns from end users that would be mainly the battery range and charging time, but at the same time working on more sustainable and efficient electric vehicles. So we aim to contribute in the meeting the targets for greenhouse gas emissions reduction in Europe, while boosting the acceptance and the take-up of electric vehicle. Okay, how we aim to do that? By increasing the energy density, so reducing weight, working on lightweight designs and concepts in the whole design of the battery, except the cells. So our project was not focused on cells. We focus on all the other systems except the cells. Okay, optimizing the battery system's performance, so increasing the battery range, reducing the charging time by improving the thermal management of the battery, so increasing the battery lifespan, tackling the degradation of the cells, and reducing time and cost for manufacturing and maintenance, and also in testing. Okay, these were some of our targets. At the end, we aimed to bring some innovations to be able to design batteries that are easily or facilitating the repurpose for second life applications, and with all these actions, reducing weight, extending range, lifespan, etc., reduce the environmental impact. Okay. Now, as you will see, there are many things that have been many innovations within the battery pack of MARBEL. Battery pack of MARBEL is a prototype where we tested the implementation of these innovations. So design, lightweightening, recycled alloys in the housing, wireless bus bar, wireless communications, the enhancing the thermal management, the BMS, a modular BMS concept. Also, all these have been worked, and then to build a prototype and also work on the test procedures at cell, module, and pack level, the validation in a modular and versatile platform, the electric vehicle in the loop, in IDIADA, and also working on a safe dismantling. Okay, in this case today we will address the circular design in the battery and also the dismantling bar. We have been working from 2021, and now this month we are ending. We built our prototype, battery pack prototype. We presented last week in Torino in CRF, and well, we are in our last week of the project. This is a video I wanted to show that we made for last week. We presented in Italy. Where we present a bit the storyline of the project, starting from the requirements for the battery that were in the initial part of the project, then identifying and applying ecodesign methodology that will be explained later by my colleague Violeta. And this methodology allowed us to identify hotspots and build together with all the partners ecodesign actions. Then we proceed after designing the battery in the manufacturing of the different components of the battery. You have seen the housing, and then assembling, providing all the components and assembling first the modules. You can see one of the modules with the assembler, electronic components, and the whole pack with the whole thermal management system. Rails, the junction box, the electronics of the BMS, and the components like the Smart Cell Manager. We also worked in testing, as I commented. This will have been presented in last week, and the presentations are available in our website, and also in the platform, the testing platform, electric vehicle. So now it's time to move to the first presentation that in this case will be presented by the group chief scientific officer of SKTS, Mr. Farouk Tedjar. He's founder of the first recycling startup in Europe in 1994, so incubated near Polytechnic Institute of Grenoble in France. And since up 25 years, is operating in battery recycling and have confirmed 4 patents in this time. Okay, so the technologies have been disseminated worldwide: US, UK, Spain, Poland, Singapore, and he's former president of the French Battery Recycling Association and member of the European Battery Recycling Association. So Farouk will present us what have been done during the project in what concerns safe and efficient opening and recovery of the battery packs. Okay, so I would say the floor is yours, Farouk. Thank you for coming.
Thank you. Thank you for your kind introduction. Do you see my screen?
Yes, but not in presentation mode. If you can.
Okay. Sorry.
Let's see if it works.
It's fine now?
Yeah. Yes. Now we can see in full screen. Thank you, Farouk.
So now I will present just a summary of the dismantling and management of end of life or second life, and two very important key for the second life is non-destructive pack opening, which is another subject. And thanks to MARBEL project, we apply for a patent. Patent is already granted in France, and extension in Europe is in progress. But beside this, you have to make the electrical control of health for the site, second life of module, second life of cells, or if you are below the threshold, the fixed value, then we go to recycling materials. So this test is a key. But you need also to take account that the cells are subject to the second life. This means that you need to make non-invasive method. Otherwise, if already you ask some capacity from the module, then you will compromise the next quality of the cells. So we develop electrochemical technique, which is not new. It's largely used in the electrochemical lab, but in 3 electrodes, we apply to 2 electrodes. Is an application of the pulse current during time 2, and then we stop the pulse, and we see the relaxation voltage. Then when you record the OCD voltage and the relaxation voltage after the pulse, you will have 2 parameters. The first one is the ohmic drop, internal resistance, and the second one is the over voltage. So both parameters, the ohmic drop and the over voltage, they are both connected to the diffusion layer of a diffusion speed and kinetic of the lithium. Don't forget that this battery is named lithium-ion battery. This means that the driver is lithium-ion and the diffusion is lithium-ion. And just for the story, at the beginning, these batteries was called rocking chair batteries, but now they forget this word, but I like a lot this word, is rocking chair, because the lithium is moving from one side to other side during discharge, and from the other side to the back side in recharge. So the key parameter is the diffusion of the lithium ion. So we have adapted the commercial product, but we enter a proprietary software to manage this sequence. And then for the cell or the module, this one is the module of MARBEL project. We make the evaluation of the CD state voltage, open circuit is 22 from 90, 85. And then we make the pulse at 40, which is almost C. And then we follow the relaxation. Then we have the ohmic drop and we have the over voltage. And In terms of capacity, during this pulse, we use only 0.33 amp per hour against the nominal capacity 114, which is 0.2%. We are really in non-invasive condition. But what is very important is to evaluate the state of health. This means that one pulse gives you the absolute value, but not information on the cells in the time. So you need to make several pulse, 30 seconds, and you follow the initial voltage with the deviation of the alpha angle, and we also follow the end of the pulse voltage, which is another, it is not flat, there is another angle, which show a deviation from one pulse of 30 seconds to the other one. So if there is a deviation in 30 seconds or 60 or 90 seconds, 3 pulse, this means that the state of health is absolutely not so good that we believe. So this can come from several parameters in the lithium-ion chain. The first one is we can have some corrosion on the copper or the aluminum. So the corrosion of the copper in front of the graphite anode, or the corrosion of the aluminum in front of the oxide, metal oxide like NMC. And we can have also some precipitation at the interface between the separator and the electrode. And the last possibility is to have some dryness of the separator, which block the diffusion of lithium ion. So all those parameters, they have to be defined by post-mortem opening of the cell, but at least you can detect without opening the cell. So we make several tests on several batteries to have an algorithm, and still in progress. Is beyond the project of MARBEL because we need more time. But we are working on the cells recovered from the battery pack of MARBEL. So now we develop a second approach, which is also very well known in all the electrochemical lab for state of charge and state of health, is impedance spectroscopy, but using only 2 electrodes, which is completely a challenge before the classic impedance spectroscopy using working electrode, auxiliary electrode, and the reference electrode. Here, the auxiliary and the reference electrode are short circuit, and we control against the working electrode, which is the cathode. So general spectrum is semi-circle with slope, and also you make the imaginary value of the impedance equation to real value, and then the variation is acquired for each frequency. So when you make for the cells, for instance, the first cut of the cycle to the axis of the real is the internal reference resistance. The second cutting is, so for the reference, lower is battery the state of health. The second one is the capacity effect, which is the top of the cycle, and there is some equation which can determine some electrochemical parameter of the capacity. And this is linked at the difference of the internal resistance. This is linked to the state of health and state of charge. And after we have the right, not circle, and this is referring to the solid state and diffusion of the lithium ion into the electrolyte and into the anode or the cathode. And the angle higher than 45 degrees indicate a poor diffusion of lithium. And finally, the second cutting of the cycle to the axis of real value is the charge transfer resistance. Higher is the charge transfer resistance, poor is the state of health because the diffusion and the kinetic are compromised. So this is really a fast method and also non-invasive because we can do it at C on 20 and at frequency variable. And then you can have very, very interesting information, including the last one, which is the inductive loop, which indicates the contact of the copper, because if the contact is very close and very smooth, the loop is small. However, if it's higher, this means that it's passivation and corrosion of copper and aluminum. So it's a really very performant tool to characterize electrochemical cells as the cells of lithium ion. So the technique is normally combining a frequency generator and potentiostat. So these are generally produced by two companies and different equipment. And we collaborate with the startup coming out from Polytechnic Institute of Grenoble. And we are in progress to make a new equipment which combine the scanning in impedance from 10 megahertz to few millihertz and the pulse. So this device will be dedicated to cell testing. Thank you very much for your attention.
Okay, thank you. Thank you very much for the presentation, Farouk.
Yes, pleasure.
Okay, there were one question from the audience.
Yes.
That I see. Well, someone was asking at the beginning if the state of health has been monitored per cell for second use. And at least
we do it in MARBEL. We do it by module, but if the module is not good, then we dismantle the cells and we do it by cells, because maybe one cell is not good and the module is not good, but 11 cells are good.
Okay, perfect. Okay. Then someone else want the occasion to ask a question to our speaker, to Mr. Tejjal. I was wondering whether on the competitive advantages that give these new innovations, no, in what concerns the business of recycling, what advantages provide, like saving, for instance, if it saves time, or also if even permits to increase the ratio of materials recovered later on from the cells. Have this any influence?
Yeah, there is an influence of the productivity. You know, if you make, let's stick only with the first period. If you make 5 pulse of 30 seconds, it's 150 seconds. After that, you can have the algorithm and the conclusion, and you don't need to discharge totally the cells in order to know what is his really capacity, etc. And secondly, it's very important that you make the economy of processing, because even if the cells or the module is not good for the electrical car due to the need of power and performance, but it's very, very important to dedicate it to the storage, like storage from solar energy or something, that we have developed in MARBEL project. We have developed an energy storage system, mobile. You can use it in the framework and construction in the highway where there is no electricity. At least you can use this module or this
Hmm.
pack to charge the mobile phone, to charge the computer, to have some light. So
Hmm.
you make a lot of economy. And
Okay.
finally, you make economy in recycling because recycling cost energy, chemicals, etc. So you don't send to recycling cells, even if they are 50% of state of health. 50%
Mm.
is not valid for mobility, but is valid for a lot of other applications.
Mhm. Okay. No, no, it's good to point because I think there are big advantages on this and that enhance the possibilities of recycling and recovery. In fact, there were one person in the audience that was asking about the impact of the costs of tests to be applied against the selling price of the second life batteries.
Now, the test is really
Mm.
150 seconds is not
It's
impacting a lot, but
okay.
it's a guarantee. It's a guarantee that you can. But the 90% of the value is the material content, mainly the
Mhm.
lithium, the nickel, and the cobalt.
Mhm. Okay.
Obviously, if you want to make a circular economy, you need to make also solidarity economy, and then you
Mhm.
can sell it as acceptable price
Mhm.
to substitute other source of energy in terms
Yeah.
of CO2 emission. And
Yeah. That's true. Okay. Great. Very, very interesting and well, really thankful for
my pleasure.
coming here. Was very interesting. Thank you, Farouk. We will move
Thank you.
to the next presentation then, and thank you for
Thank
the
you very much,
questions
Mark.
from. Okay, thank you. And the next presentation, what we planned to present is what concerns the eco-design in MARBEL. So how we applied the eco-design principles when designing our battery. Okay, and this presentation will be this topic will be presented by Violeta Vargas, that he is advanced researcher at the Waste Energy and Environmental Unit in Eurecat Technology Center. Okay, Violeta holds a Bachelor in Industrial Engineering from the University of Sonora in Mexico and a Master's in Natural Resource Engineering from the Polytechnical University in Catalonia. He holds a PhD in Environmental Science and Technology from the Autonomous University of Barcelona, and she has been involved in environmental impact related topics for over more than 10 years, particularly in what's the application of the life cycle assessment methodology, okay, and particularly in circularity in batteries, and he's also teaching in the university about this domain. So nice to have you today here, Violeta. The floor is yours to introduce this topic.
Thank you, Eduard, for your kind introduction as well. So first I'm going to explain why we're doing here, or what are we doing and why we're doing it in MARBEL as well. As you know, greenhouse gas emissions are, well, we're trying to reduce all greenhouse gas emissions. And for this, we are still having lots of emissions coming from the different sectors. And you can see it on the screen how transport has a share of 16% of the total emissions in the European Union. So if we focus on improving this 16% of the emissions coming from transport, it would be a great improvement in the global share of greenhouse gas emissions. So basically, well, explaining a bit behind what happened before is that MARBEL emerged with a profound commitment to address these pressing challenges that are faced by especially the automotive industry when it's pursuing this decarbonization and reduction in emissions, environmental sustainability, and such. Um, we started first with the Paris Agreement, which is a global commitment to reduce emissions and to maintain the increase in global warming below 1.5 Celsius degrees. And with this, a reduction on emissions to 2030 and zero emissions by 2050. And then we have also the European Green Deal and the Fit for 55, which are plans and more strategies to reach these goals as of the Paris Agreement, right? So with this, we came up with MARBEL. Well, MARBEL came up to try and solve these problems or to tackle this, to provide a solution through a versatility concept, which means it's going to develop the solution, or it developed the solution of this battery pack, fitting with the four categories of the circular economy, which is the design and production, the use, the recovery of value models, and the support, circular support models as well. This project focuses on a modular design with wetless connections, a safer disassembly with a structured plan for it that will also improve the possibilities for second life of this battery pack or the components, an improved cooling system, a more flexible, versatile, modularly best test bench as well to do all the testing. And well, for this design of this battery pack, what we did was applied this eco-design methodology that was developed by Eurecat, which includes four very easy steps to follow. The hotspot identification, strategy definition, readaptation of technology or technological aspects to these strategies, and then a definition of specific actions. And all this accounting for, first of all, the life cycle assessment as part of the eco-design methodology. With this, we have data-driven insights to find the hotspots, to identify where we have to really reduce the impact so that this is relevant in the improvement. So again, explain a little bit more on this eco-design methodology. We have the first stage based on a benchmark analysis of battery packs with the application of life cycle assessment and life cycle costing in a prospective way. Then, after having these results, we identify the hotspots and we establish the most properly eco-design strategies that we could apply in any battery, let's say. But then we had to make sure that these different strategies were actually applicable in our project at the level that we are trying to improve and at the level that we can produce things. So we did some workshops with the partners of the project, and we aligned these different strategies with the technological procedures, the possibilities technically, the technical possibilities, and we defined a set of specific actions. So a bit to explain how we did this benchmark analysis gave us some insights on the hotspots, and we prepared these different slides for the different life cycle stages so that we can share these different slides with all the partners or stakeholders to find the strategies that could be applicable, that would make sense and make a real change in the environmental or cost impact. After that, as I said before, we defined the most properly eco-design strategies based on these hotspots, and we also prepared this sheets, a data sheet for each of the strategies, including the impact that it would have in the different life cycle stages of the vehicle or the battery pack within an electric vehicle. After that, we aligned them to the technological procedures, and we eliminated some of the strategies that we proposed at the beginning, ending up with 10 final eco-design strategies to be applied. And after this, again, after a few workshops with the stakeholders, we defined 14 specific eco-design actions to apply in the battery pack of MARBEL. After doing this, then we can compare all the results of the preliminary assessment that we did at the beginning to find the hotspots and to then later improve the impact and compare it with the results of the MARBEL battery pack after the design and definition of it. So after performing a new life cycle assessment on the MARBEL battery pack, we have this comparison with a reduction of 27% of the impact per kilometer, or yeah, and this can be also calculated as a reduction of 16 kilograms of CO2 equivalent per each 100 kilometers that the vehicle of the vehicle life. We also found some insights on this assessment that mainly the impact is coming from the battery materials. So as much as we can reduce the materials that are entering the battery pack, and this can be done by lightweighting, but also by including recycled content in this battery pack. This would give us a bigger reduction on the impact. Then the second share would be the use phase, because it's also consuming time of the vehicle. So again, if we make it more lightweight at the beginning, then the vehicle will consume less fuel or energy during the lifetime and increase the lifetime of the vehicle. And this would also reduce the impacts in a very big percentage. So just to give you a hint on what this means, 16 kilograms of CO2 equivalent. If we reduce this, we can also think of it as reducing 2 days of an average household consumption, or stop eating 8 beef hamburgers, or 15 minutes of flight. So it's a considerable amount that is being reduced. Maybe it doesn't sound like a lot, or maybe it sounds like a lot when you say 16 kilograms. You don't know how to relate it. So this would be the translation to our daily life. After doing all these calculations, then we recalculated, and then we redesigned these Excel sheets or spreadsheets with all the information for each of the eco design actions. And we have this other sheets with the results. So for each action, we have all the information, what it entails, the challenges faced by the different stakeholders that had to apply it, and then the life cycle stage and how it affects the different life cycle stages, as well as how much was able to be implemented, and the benefits to the environment, and some conclusions of the application of this. I'm just showing a few of the slides of the results, because we have this the results for each of the components of the battery pack, but we don't have the time to show it all in one session. So first of all, for the general battery pack, we have the application of the different 14 strategies, and you can see them on the x-axis. It's by number. So A10 means a higher lifespan. A1 is the recycled content of aluminum, reducing the raw material extraction, and so on. Some of them are reducing copper and changing it for aluminum. Another ones are focused more on the wireless part. But you can see how much each of these strategies or actions, sorry, are reducing the impact, and at the end giving a total of 8,000 kilograms of CO2 reduced. In this case, we're presenting kilograms of CO2, but you'll see that in some cases we're presenting other impact categories, because we did an LCA with more than one impact category. It's not only a reduction on CO2 emissions, but also on toxicity and other impacts. So for this, we are presenting here, or highlighting, that the main actions that are reducing the impact in this battery pack are the use of recycled content in the battery pack, and also an enhanced BMS that provides a bigger lifespan of the battery. And this is mainly the reason why this battery pack of MARBEL is a lot more efficient and less. It has less impact on the environment than the baseline that we used at the beginning. Another way of presenting the results is per component. So in this case, we're presenting the housing profiles, which is one of the main contributors to the benefit in environmental impact. And for this case, the main actions that are making a difference are the use of recycled and recyclable materials, because it was a substitution of 60% of the aluminum per recycled aluminum, and also the reduce of quantities for soldering parts that allows also for a recoverability of the modules at the end of life, as Farouk was saying before. Um, so it's a reduction here. Only we're talking about kilograms of CO2 or climate change of 1.56 tons of CO2 saved per battery pack during all this useful life. Okay, we're not talking anymore about functional unit of kilometer. We're talking about the whole life of the battery pack. That in the case of MARBEL, we are accounting for 300,000 kilometers and a second life using it, the modules, using it as scooter. So then another example would be the junction box that is also accounting for some amount of recycled and recyclable materials, a reduction of copper that was changed for aluminum, that is also reducing the weight and the content of copper that is as let's say a special material because it's almost a critical raw material. And it's also this junction box provides also the possibility to increase the lifetime of the battery pack. So with this junction box, it provides a 19 kilograms of CO2 that are saved, and it's also 1.2 tons of I forgot the name of the this compound that is for human toxicity on the right, on the graph on the right. What else? Well, then I have only the conclusions now. We were through ecodesign, we were able to identify the hotspots and to reduce the key environmental concerns with the lithium-ion batteries in electric vehicles. Through this collaborative work with all the stakeholders, we were able to define 10 generic eco-design strategies and 14 specific eco-design actions that led us to an environmental impact reduction of more than 27% in all impact categories per each of the kilometers during the useful life of the MARBEL battery pack. Well, that would be a very summarized result of the MARBEL eco design aspects. But if you have any more questions, I'm available for later communication.
Great, thank you, Violeta. And as Violeta said, this is just a part of the. There is a number of actions that have been taken in the design. And in fact, MARBEL plans to deliver some public deliverables, and in one of them these actions will be listed. So at the end of the project, once we close in the next months, you will have a document with the list of actions that have been applied into this project. So thank you very much, Violeta, for the presentations. Since the next three sessions, I think, have some relations, I would bring the questions to the end, okay, from the audience. I will collect them. So we can proceed with the next presentation that will be presented by Tony Lara concerning the design, easy to disassembly battery pack design. Okay, Tony Lara is a researcher at the Product Innovation and Multiphysics Simulation Unit at Eurecat Technology Center. He has a bachelor's degree in mechanical engineering and a master's degree in material science and product design. Okay, he is a researcher at Eurecat since 2005, so he has more than 20 years of experience in materials technology, manufacturing, transformation of materials, methodologies and processes, mechanical, and also special in what concerns the mechanical properties of the materials, no, formability, wear, impact, fatigue, behavior, etc. So he have been leading the unit. This unit have been leading the design of the battery, and Tony is also involved in other research and innovation projects related to the design. And well, he will be presenting the design of battery, so of MARBEL battery. So Tony, please, the floor is yours.
Okay, thank you, Edward. Do you see my presentation, right?
Yes, we
Yes?
can
Okay.
see it in full screen, so perfect.
Okay. Okay, thank you, Edward. So I will introduce you the design of the battery. Okay, the idea is to explain a little how we manage to design and also prototype a modular and easy to assemble and disassemble battery pack. Okay, so this is the MARBEL battery, okay, and the idea and the innovations that we introduced in this battery was the fact that this battery is modular and we can adjust and build different batteries for different vehicle segments with the same idea. This battery is also lightweight because we use we use a lightweight material as the aluminum to build not only the battery housing, also the module housing. Also, this battery is thermally optimized. So we introduced some innovation regarding the thermal management system of the battery. Okay, regarding the cooling not only of the cells, cooling also all the bus bars and electronic parts of the battery, with the idea to reduce the degradation of the cells and so increase the lifespan of the battery. And finally, this battery it's also easy to assemble and disassemble, not only to increase the repairability of the battery, also to improve the second life and also the end of life of the battery. In this presentation, I will focus in the modularity of the battery and in the idea of easy to assemble and disassemble. Okay, so here do you have the battery without the top cover? Okay, and here we can see the housing of the battery pack. Okay, that it's all from aluminium. Also the modules of this battery, where there is the cells and also the electronic components that manage the cells. The cooling system that, as I know, I explained, it's composed for two parts. Okay, the bottom of the housing that it's to cool the cells of the battery, and also these cooling channels in the top of the battery, that the idea is to cool not only the bus bars, also all the electronic components of the battery. Then there are all the electronic bus bars of the battery, all the electronic components, and finally the connectors to the motor and also to the charger of the battery. So regarding the modularity of the battery, we design and also prototype two kinds of battery. Okay, one battery of 800 volts and one battery of 400 volts. And the idea is to try to use as many components as we can. And in this case, to build these two different batteries, we use the same aluminum profiles, okay, not only for the bottom profiles and the cooling, also for the lateral profiles and the turrets that keep the top cover attached to the frame. And the only different part in these two batteries is the profile length and also the machining in the front profile. Regarding the modules, okay, we use the same modules with the same electronics for the two batteries. And so the only thing that changed from one kind of battery to the other battery is the number of the modules. In case of 800 volts battery, we use 32 modules. And in case of 400 volts battery, we use 16 modules. Regarding other the electronic bus bars, the electronic components, and the connectors, we use the same bus bars between the modules, okay, between all the modules. We use also the same electronic boards inside the modules and also for the battery management system, the same type of connectors and the same DC box. And in this case, the only things that change from one battery to the other battery are the bus bars to the junction box, because the junction box it's different, and also the number of connectors and electronic boards. Regarding the cooling system, we use the same cooling system for top and bottom cooling. Okay, and the only thing that changed from one battery to the other battery was the length of these cooling channels. Also use the same cooling distribution, okay, that it's attached to the housing of the battery. And finally, regarding the cover, also we use the same aluminum sheet and the top cover stiffeners profiles. And once again, the only thing that changed in this case, it's the length of the sheet and the profiles, and also the number of profiles to stiffer the battery. So regarding the easy to assemble and disassemble, okay, regarding the battery pack, here we have again the housing, okay, we use the same housing, and the housing includes the cooling, okay, that it's with the bottom profiles, and in this case we use 60% recycled aluminum, and all the housing, also the turrets, are manufactured from aluminum. Regarding the modules, okay, we attach the modules. All the modules are screwed to the housing, okay. Also, the electronic bus bars, the electronic components, and all the connectors are bolted to the battery and to the module, so we can remove easily, okay, to repair or to change any module in any situation. And finally, the cooling system. Regarding the distribution of the cooling system, is screwed to the housing of the battery, and the top channels are supported by the modules, the top lid of the modules. And finally, we screw the top cover, and also the top cover is screwed to the housing of the battery. And the idea is to use the same procedure, but as in reverse, for the disassembly. Okay, and then we can open the battery, we can change anything we need without cutting or breaking any component, because all the joints are bolted. Okay, regarding the module, okay, we use in the module 12 cells. Then we use cooling fins and cooling pads to translate the heat of the cells to the bottom part of the battery, okay, that are cooling. And finally, we use compression pads. Then we introduce the module housing. In this case, all the module housing, it's also made from aluminum, okay, and all the components of this module housing are screwed so it's easy to assemble and disassemble. Then we introduce all the electronic bus bars and all the electronic components, and in this case also all these components are bolted, and so we can dismantle easily. And finally, we screw also the top cover, okay, of the module, and this top cover it's needed for the cooling of all the electronic components and the bus bars, and it's also screwed to the housing. And in the same way that in the base in the battery pack housing, for the disassemble of this module, we can use the same procedure, but in reverse. Okay, so, and more or less, this is all the information regarding the battery that I want to show you.
Great. Thank you, Tony. Thank you very much for showing all these implementation of actions, in what concerns facilitating especially in what concerns the facilitating this disassembly, so repurposing of components for second life, that have one big impact on the overall life cycle of the battery. Okay, and now after this presentation, we wanted to tackle the topic of the life cycle cost in electric vehicle batteries. Okay, For this, we invited Ana Sanchez from the Institute of Research from IREC. Okay, it's the Catalonia's Energy Research Institute. And Ana Sanchez is working as project engineer in this institute and is participating in European and national projects carrying out life cycle assessment, life cycle costs, social life cycle assessments in the field of renewable energy, energy storage, etc. So she has teamed up with Violeta in this part of the assessment in what concerns life cycle costs. So happy to have you on board, Ana. The floor is yours.
Thank you for the presentation, Eduard. So it's a pleasure for me to be here today to talk about the life cycle cost of the MARBEL battery. So first, let me start with some figures about the economic aspects of the lithium-ion batteries. The graphic we have on the left-hand side illustrates how batteries packed of electric vehicles can account between 35 and 50% of the total cost of the vehicle. This range is mainly due to a high variation in battery cost, since economies of scale can be triggered depending on the total number of vehicles produced. Therefore, the battery cost can vary depending on the number of units produced. The graphic on the right-hand side shows the evolution of lithium-ion battery packs between 2011 and 2030, with a decreasing cost over the years. The deployment of the electric vehicle fleets, the expected large volume of batteries, and the technology developments are the major drivers of the production cost decrease. Now, what do we mean when we talk about life cycle costs? The life cycle cost is a comprehensive economic assessment that looks beyond just the upfront cost of a product. Instead, it accounts for all the costs throughout the entire lifespan of a product, from manufacturing to the disposal. This approach is particularly important for electric vehicle batteries, as their cost effectiveness is not just about how much they cost to produce, but also how efficiently they perform and how sustainably they can be recycled or repurposed. Understanding the LCC is essential for several reasons. First, it enables cost-effective decision-making for both the manufacturers and the consumers. It supports a sustainable and circular economy, reducing waste and maximizing resource use. It helps policymakers and investors assess the long-term economic viability of different battery technologies. And it drives innovation, encouraging the industry to explore new materials and designs that enhance performance and while minimizing the cost of the battery. Now, as mentioned in the introduction of the project, the objective of the MARBEL is to design, develop, and demonstrate a new modular, compact, lightweight, high performance, and flexible and robust BMS. To demonstrate the improvements from an economic perspective, we need to define a baseline scenario to compare it. In this case, the commercial battery has chosen is the one used in the Audi e-tron. There are three types of LCC: conventional, environmental, and social. For this project, the environmental LCC has been chosen due to its alignment with the LCA regarding the goal and scope, the functional unit, the system boundaries, and the methodological steps. The scope in the project is established as a cradle-to-gate and cradle-to-grave. In this sense, two functional units are defined for each approach: a functional unit based on the vehicle's travel distance for the cradle-to-gate approach, and a functional unit based on the delivered energy throughout the battery's life for the cradle-to-grave approach. As we perform an environmental LCC, the externalities or monetary value of the environmental and social impacts are outside the system boundaries. Now, how do we calculate our LCC? So the methodology we have used has been developed following the guidelines of CETAC and their environmental lifecycle costing framework. To correctly measure the lifecycle cost of the battery, we have considered the future developments and inflation that occur during its life, and we have introduced the concept of the net percent value. The LCC has been calculated by adapting this equation you see here in the presentation to introduce the assessment of the first and second life of the battery. Now, let's talk about some results we obtained in the project. So for the cradle to gate results, the LCC has a total value of 44,937 euros, or a 0.150 euros per kilometer. As you can see, the manufacturing stage is the main contributor as we expected. The manufacturing cost includes the cost of the purchased items and the cost of the components produced by the project partners, which account for the materials, the energy consumption, the transport, and the labor. As for the use phase, the cost comes directly from the energy consumption to charge the battery. If we analyze the manufacturing phase in detail, we can see how the cells have the highest contribution with a 39%, followed by the module and the ISCM. Within the module, we can see how the components of the BMS account for more than 50% of the cost. So we can say that the modularity feature incorporated in the MARBEL to track each module individually increases considerably the cost of the battery. Now, from the cradle to grave results, here you can see the cost for each life cycle phase, where the cost of the second life includes the dismantling of the battery to a module level and the energy consumption during the use in the second life, where we have assumed that a module is used in a scooter with a useful life of 5 years. The end-of-life stage includes the transport to the facility center and the dismantling of the battery. Since we are performing a cradle-to-grave and not a cradle-to-cradle analysis, the recycling cost is not included in the scope. So overall, we have a total cost of 46,990 euros, or a 6.55 euros per kilowatt hour, considering the total energy delivered by the battery over its whole life. Now, from this point, how can we reduce the cost of the battery? So, since we had some issues with the cells purchasing, its cost can be considered higher than the standard marketplace. So we consider to introduce the cost of the cells or the baseline, the Audi e-tron, and in this case, if we use these cells, we can achieve a 22% cost reduction. Another aspect to mention is that the MARBEL battery is designed for easier dismantling for recycling. So in this case, some materials can be recovered from the battery and sold in the second market. So if we consider that we recover steel, aluminum, and plastic of the battery, we can obtain an additional revenue of 160 euros, excluding the cells. So if we recycle the cells, we can obtain an additional revenue. And then extending the battery's life by giving it a second life is another way to obtain credits. So we consider that 50% of the modules of the battery are in good condition after their phase life. So if we consider that the 50% of the batteries can be used in a second life, as I mentioned, in a scooter, we can discount the cost of the scooter of a battery, obtaining a total of 3,200 euros of revenue. So in total, we can account for a cost reduction of 28%, obtaining an LCC of 36,600 euros, or a 4.72 euros per kilowatt hour. Now, one of the biggest challenges in assessing the viability of next-generation batteries is ensuring that the life cycle cost analysis reflects real-world conditions. So comparing a prototype battery's cost structure to a commercially available battery without considering scaling effects can lead to misleading conclusions. With a max production of batteries, the manufacturing cost decreases due to the economies of scale, process optimization, and bulk material sourcing. So we can estimate this cost reduction using economy of scales formula that I present you here. So using these equations helps predict how product volumes affect cost reduction with typical scaling exponents between 0.6 and 0.8 in battery manufacturing. Now, in conclusion, I would like to remark that the LCC analysis is a critical tool for evaluating the total cost of electric vehicles batteries throughout their life cycle. This approach provides a more accurate economic perspective, helping manufacturers, policymakers, and consumers make better informed decisions about battery investments and market adoptions. Then the revenue from the battery recycling and second life application plays a crucial role in enhancing the long-term economic feasibility of these batteries. And last but not least, scaling up from prototype to commercial production allows to a realistic compare LCC values, reducing uncertainties and enable more competitive market for electric vehicles batteries. And that's all. Thank you so much for your attention.
Okay, great. Thank you, Anna, for this presentation and for detailing the advantages of using these methodologies when assessing the cost of this kind of systems, complex systems involving many different components and battery systems. Okay, well, now we arrived to the end of the presentation, so it's time to take questions from the audience. Okay, you can write. So I invite the present Anna, Tony, and Violeta to be present, and we can establish a kind of round table to take questions. I've seen that Violeta have been answering some of the questions about.
Well, since they were there, I was trying to answer, but maybe I don't know if I completely solved the doubts because writing is different than talking. So maybe the ones that were asking for questions, maybe you have more doubts or you want to go through any detail of your questions. The first question was for energy for testing. That
considering the energy of.
We did include this in the assessments for both for life cycle assessment and for life cycle costing as well. We consider all the energy and materials that was used during all the life cycle of the battery pack. So at the end of life, there was some testing. Well, for the disassembly and testing, there was also some energy consumption, and it was included also in the assessment. I don't know if there's any more comments on this.
I remember Farouk commenting, and Mr. Techer, no, Farouk Techer, commenting that these tests, at least on the perspective of costs, were very short in time, so they will not have a big affection. So I guess, well, also in parts of impacts was not very relevant, but in any case, we need to consider, of course, and it has been considered.
We didn't have the time to present all the results in detail for the life cycle assessment in this session, but for as I said before, the raw material extraction and manufacturing are the biggest issue, and then the use stage. But the end of life was a minimum amount of energy, so a minimum impact on the environment as well.
Okay, great. Then there were questions about the useful life that we considered, no, for these 300,000. You explained this.
For the second life, I think Anna was also mentioning the life of the second life of the battery pack. In this case, we consider that 50% of the modules could go for the second life, but we are doing a sensitivity analysis as well because we know this may vary in real life or in different batteries. So maybe 50% could be the average of what can be used for a second life in these kind of batteries, but we'll do a sensitivity analysis to check if this is a big issue at the end on the environmental impact reduction that we are counting after extending the lifetime of the battery. So it's actually extended in the first life because the baseline was considered to be 160,000 kilometers from the e-tron, and then MARBEL has 300,000 kilometers for the first life, and then a second life for the scooter.
Okay. But at the end, I think maybe could be interesting to summarize a bit how this methodology, that was defined in the project, this eco-design methodology, that how it integrates the life cycle assessment and how this improves the sustainability of the electric vehicle batteries and also contributes to the circular economy policies and economy initiatives that are nowadays in Europe.
Yeah, I mean, this eco-design, it was actually an LCA-based eco-design methodology. So we use this LCA at the beginning of everything to like see where to focus, because you can't just try to improve something without knowing what you're dealing with. But then all the process with all the designers, that's like everybody working in this project, like Tony and all the other thermal management system, everybody was counting on the LCA for the different components of the battery pack to make it the best option in sustainable terms, the less impact on the environment. So it's like an iterative process that we go through all the materials and decisions to make it the best decision at the end. And I think this also will help with the battery regulation at the end, with the European battery regulation, because, well, for automotive sector, this can help also to not only report on the emissions or the environmental impact, but also to reduce the environmental impact at the end.
Okay. Well, now I see the audience is starting posing questions. Yeah, so, okay, Anthony answered one, no? Well, there was this first question about the adding features for the assembly, if it can increase the cost of the battery pack. So, will the vehicle manufacturers get any benefits from second life of batteries, or will they be forced to do it due to the ELV legislation? Maybe Richard Ellis wants to comment. Okay, okay, I thought he was opening the mic because I see that Marina tell them. Well, if the question is clear, someone wants to comment on this. And if not clear, we can ask Richard to clarify.
Yeah, this is a key issue here, because it is true. We were expecting an increase on the environmental impact as well, because of all these features for disassembly. Sometimes it entails a higher cost or higher even materials, so that at the end you can recover the biggest amount of it. I don't know how to.
Okay. No, I see that Tony was mentioning something.
Yes, as Richard said, no, the fact that we introduce these features, no, regarding the assembly and disassembly, and for example, the bolted joints, no, we have to introduce a great number of bolts and screws, and also we have to let a space, not to fix and to fix and remove the components. So probably we will have a bigger battery, so a battery that maybe it's lower than a battery with a welded connections. So I think that there is the environmental benefits, but also maybe it's necessary some regulation, to increase the circularity of these batteries, to force the manufacturers to design the batteries in this way, because the options and the innovations to perform this kind of batteries is already ready. So I think that the idea is to increase the manufacturers of batteries that try to use or try to design the batteries in this way.
Because why do you think the batteries that are part of the batteries that are currently, some OEMs are maybe taking other directions, but nowadays currently the main part of the batteries are not designed for an easy disassembly and disassembly? Why do you think this?
Why? Maybe for these reasons that Richard pointed, because maybe we have to introduce more weight, or maybe we will have a battery bigger than the battery with a welded connections and with less space to fix and remove the components. So probably these other features are more important for the manufacturers that the fact that the battery will be easy to assemble and disassemble and easy to repair. But as in other markets that maybe some regulations force to recycle more, maybe I think that in the future these regulations will be also come for the automotive industry. So I think that the manufacturer has to be prepared, has to be ready to try to design in this way the batteries.
Okay,
Yeah, you're completely right. For now, battery regulation is, let's say, it's ending at the manufacturing stage. So after that, or maybe even use stage, because you can account emissions per kilometer or per kilowatt hour provided, but then the disassembly is not included. So it should, yeah, you're right.
Yeah, so I think it's a combination between research and policies, in this case, and also I think takes a big role, the end user, as the ones that will be using the battery. So the cost that arrives to the end user, and for instance, in what concerns the impact of the life cycle cost in the adoption of the batteries. And also, I know maybe Anna, you can give us some opinion on how this life cycle cost affects the impacts on the consumer adoption and the market competitiveness.
Yeah, of course, if we have a lower LCC, obviously it's more attractive for consumers and market adoption. So by reducing the total ownership cost over time of the battery. So if we optimize the battery design and improve its efficiency and also incorporate second life applications, we can try to reduce the cost of the battery. So by implementing these new features, we can try to reduce the cost and enhance the market competitiveness of these new batteries.
And I also can imagine that if we if we go further than just the manufacturing, but we consider the second life in both what concerns the environmental impacts and cost, etc. This is something, I don't know what Violeta was commenting, that the regulations are stops on manufacturing, but if we consider the second life, things change and in what concerns impact and also economics in these both aspects. Okay, we can, Violeta, you want to comment? Yes.
I see another question.
Yeah, there is a question from the LCA.
Okay.
I wanted to put it on the table now. That if there were this one about if we had the opportunity to compare weight and LCA LCC, MARBEL module with similar size market available solutions. Yes, this one is interesting.
Well, first of all, hello Claudio, because we see friendly names over here.
Okay.
I've seen also other friendly names in the list of attendants, but I'm glad that you're here, all of you. Yes, we have been able to compare it with other battery packs that are similar. We did actually a very thorough study on literature, and we found a few. We did an average and compare it also to this average of battery packs that were available. The weight is this one, MARBEL is heavier, but the LCA, at least the LCA, is better than the average. The LCC, I'm not sure, Anna, if you have any data on other.
Yes, for the LCC, as I commented during my presentation, right now we can give a comparison because the MARBEL battery is a prototype, and it's not fair to compare a prototype battery with a market-ready battery. So we are working to try to scale up the results from the MARBEL battery in order to compare it to a market battery. But hopefully we can arrive to at least at the same cost of the market level.
Okay, great. This this is interesting, no, to make these comparisons. We also have been working on this, no, benchmarking and comparing, and also providing some as conclusions of the project, no, summing up the eco-design actions, summing up a recommendation in policies, for instance, in what concerns the regulations on batteries. Well, I think I'm happy that MARBEL tackled this topic, and that we are bringing value to the discussion on this in Europe. There is a new question from Guillermo Mazabal about the disassembly. If he's asking if the modules and the battery case can be reused or refurbished instead of recycling.
Yes.
Yeah.
Tony.
Regarding the idea, the main idea of this design was to not only recycle cargo, also to repair the battery. So all the modules has electronic device that are informing regarding of the state of health of the different cells. And the idea is not only to change a module and to repair the battery, also to change a cell. Because we can dismantle the battery pack until a cell level, okay? Because all the connections, as I show you, are bolted, so we can we can remove these bolted joints, we can change a cell, and also we can also dismantle the bus bus connections and change and repair. So the idea is not only to reuse, it's also to repair the battery.
Okay.
That's how we were able to account for a second life of the different modules after the first.
Yeah, the modules can be directly used. They are not affected. There is the assembly, the housing. It's another thing, no? The casing depends.
Yeah. And also, I remember that all the electronic components, for example, the BMS, are also designed for a second use. So you can use the module the module to a second use, and as you don't need to break anything of the battery. You can remove this module. You can put this module in another application, and you can also use the electronic components for this second use. But also, as I say, you can repair the modules, and you can reintroduce in the battery.
Great. Perfect. So, well, I think we finished. We answered all the questions, and I would like to really thank the audience, because you were posing very interesting questions for the discussion. Okay. Claudio from Endurance is commenting that yes, he's glad to support the findings. Okay, so they came to similar conclusions with the flagship the project in IPCEI batteries project. I remember about commenting and coinciding with this project. Great, thank you, Claudio, and thank you all the rest of the audience for your questions and for participating in the project, in the webinar. Sorry. And well, the thing is that I would like to encourage you to keep in touch with MARBEL team. You can follow us in the social media, send us, contact us via email, or well, try to review what's published in the website, because all the research, all the results, all the results of the work, the outcomes of these 4 years of project have been done to have an impact in our economies and our daily life. Okay, so it's important. Do not hesitate to contact us for transferring knowledge in terms of service, for transferring all these innovations and to your batteries, your business, your research. Okay, and further walking this path for a more sustainable electric vehicles in Europe. Okay, so glad to have you in this webinar. I just say thank you also for the speakers, the organization, And well, see you in other forums and maybe projects, research projects or joint initiatives. Okay.
Thank you very much.
Thank
Thank
you.
you.
Bye.
Thank you all. Have a nice afternoon.
Thank you. Bye.
Bye bye.